Yeah, okay. Good afternoon. I'm very pleased to introduce Dr. Shimon Moody, who is a research assistant professor from the College of Technology, and he does a lot of work on biometrics, about which he will be talking today. Okay, thank you, Shimon.
Thank you, Professor Bertina. So today my talk will concentrate on analysis of fingerprint sensor interoperability on system performance, and this was part of my PhD dissertation work. And actually, Professor Bertino was one of the committee members on my PhD work, so this will be a recount for her. But the agenda for today's presentation, I'll try and do a brief introduction of biometrics and give you a little bit of an overview of what we do in the biometrics lab, so that you have a base for the rest of the presentation. And then I'll go into the problem definition, the significance of the problem that I researched, what is the purpose of the study, the data analysis methodology and the analysis methodology, and go into the conclusions and some future work. And there are quite a few interesting future work avenues that came out of it, and we are always looking for people to collaborate with. So if something interests you, then please come and talk to me after the presentation. So what is biometrics? Biometrics is defined as the automated recognition of human based on physiological or behavioral characteristics. So some of the examples of biometric technologies are fingerprint recognition, face recognition. These are the more popular ones, the ones that you get to hear about in the media. Then you get into some of the ones that you don't hear about too much, things like signature verification, keystroke dynamics. And this list is not exhaustive, but these are just some of the examples of biometric technologies. And what we do in the biometrics lab, we concentrate on applied research. We do not really work too much with basic science and development of algorithms, but we'll collaborate with other departments that will work with algorithms, and we will test how well does a particular device or algorithm work when it's deployed in the field. So we try and be the feedback loop between basic science and what happens when the particular device is deployed. So a lot of our research is very applied in nature. So when you talk about biometric systems, they can be categorized into 5 subsystems, and this is independent of what kind of modality you're talking about. The very first one is data capture. This is where the user interacts with the system and provides his or her biometric characteristic. From there on, the data is sent on to some kind of feature extraction, processing. Once the sample is processed, it's either stored, or if there's a matching operation, it is sent to the matching subsystem. And in the end, you have a decision where, based on some kind of administrative policies, you will decide if a particular matching operation is a success or a failure. So within the biometric system, you have 2 processes. The very first one is enrollment. This is where a user will interact with the system for the very first time, create a reference template for himself or herself, and from there on, every subsequent interaction with the system will be either a verification or some kind of a recognition operation. So now let's get into fingerprint recognition. Fingerprints itself are formed by the flow of ridges on the surface of your fingers, and these ridge lines have discontinuities in it, and these discontinuities are called Minutiae points. And there's a pattern that is formed by the placement of Minutiae points, which is what makes your fingerprint unique to yourself. And in terms of fingerprint recognition from an algorithmic perspective, each Minutiae point can be described using 4 characteristics. The x-coordinate, the y-coordinate, it's the direction of the Minutiae point, the angle, and what type is it. Minutiae points are broadly categorized into 2 types. It can either be an ending, where a ridge line just comes to an end, or a bifurcation, where a single ridge line will split into 2 ridge lines. So these are just some basics of fingerprint recognition and how algorithms go about doing fingerprint recognition. Just a very top level overview of how Minutiae extraction is performed. Once you capture a raw image from the sensor, it's binarized. Basically, the image is converted into either black pixels or white pixels. Most algorithms will define the black pixels to belong to the ridge lines. And once the binarization is performed, the algorithm will go through what is called skeletonization, which is the ridgeline will be eroded to the point where it's only a single pixel wide. And once the skeletonization happens, there'll be some kind of a tracing algorithm that will follow these ridgelines and identify minutia points or breakages in these ridgelines. Another issue that comes up when you talk about biometrics in the applied domain is sample quality. And what is quality? There are three different connotations. The first connotation is character. So this is where the quality is defined based on how well does the sample actually provide, or how well does the source actually provide a sample. So say in terms of your finger, if your finger is scarred, it is said to have poor character because it cannot give a representative sample of a proper fingerprint. Fidelity is based on how accurate is the representation of that sample that is captured to the source. So if a person cannot interact properly with the fingerprint sensor, the sample will not be representative of the source, so it will have low fidelity. And the third connotation is utility, which is, and you'll see an example of this later on that I used for my PhD research work, is utility is defined as the contribution of the particular sample to the error rate of the data set. So once you introduce a sample into an existing data set, what is the effect on error rates of the entire data set? Do the false match rates increase? Do the false non-match rates increase? So just the matching accuracy of the entire data set, what happens to it? In terms of fingerprints, what are some of the factors that can affect sample quality? The first one is the condition of the fingerprint itself. Depending on how dry or how moist your fingerprint is, it will provide different characteristics on different types of fingerprint sensors. Then there's habituation. How well does the individual know how to react or how to interact with the device? Nowadays, you see laptops with swipe fingerprint sensors on it. That requires a little bit of a different interaction compared to traditional devices, where you just place a finger on the device. The type of technology that's used is there are several different types of acquisition technologies. The more commercially available ones are optical, capacitive, thermal. All of these technologies introduce their own weaknesses because of the underlying acquisition methodology and the ergonomics of the device. How well is the device designed so that the person can actually interact with it? So when you talk about sample quality, obviously if you have a bad quality image, it will have an effect on the overall performance of the data set. It's a very simple paradigm: garbage in, garbage out. So these are some of the issues that you see when a fingerprint recognition system is deployed in the field. When you have unhabituated users come and interact with the device in an operational environment where there might be dirt, where people might be coming in with hands that are not of perfect quality. So now, going into the problem definition of the research work that I performed, this was more related to interoperability of fingerprint sensors. And fingerprint sensors introduce distortions and variations in the images that are captured by the sensor. And these distortions are dependent on the type of sensor, and they are not always consistent across all the different sensors. So an individual providing fingerprints on an optical, on a capacitive, and a thermal sensor will not always provide the same type of fingerprints. And if there are inconsistencies in the resulting sample, they will not be the same across all the different kinds of sensors. So when you match fingerprints that have been collected on different types of fingerprint sensors, it increases the probability of false match rates and false non-match rates. These are error rates that define the performance of a biometric system. And in terms of performance, you want to have minimal number of false matches and you want to have minimal number of false non-matches. So an increase in any of those error rates is not a good thing. So when you talk about interoperability and the types of distortions and variations, they can be broadly categorized into three different classes. The first is the interaction type. Fingerprint sensors come in two basic flavors when you talk about interaction. They're either of the swipe type or they're of the touch type. The swipe fingerprint sensors are the more common ones that you see on laptops, and the touch type of fingerprint sensors is the kind that you'll see when you come into the country at the U.S. visit program, or if you're members at PEFQ, when you interact with the fingerprint sensor on the ATM. That's a touch type of sensor. Then you have the acquisition technology type, like I talked about, optical, thermal, capacitive. These all introduce their own distortions and variations in the resulting sample. And then you have the sensor characteristics. What is the physical design of the sensor? What is the resolution of the resulting image? What kind of capture area does that particular fingerprint sensor have? These are all characteristics that will affect a person's ability to interact with the fingerprint sensor. What you see here are just sample images of the same fingerprint of the same finger that were taken across 9 different sensors that I used for my study. And if you were just to look at it even briefly, you'll see that you can see distortions and variations and in the resulting image just based on the type of sensor. And because of these distortions and variations, it causes issues when you try and compare these fingerprints. So this is just to give you some visual representation of it. So why is this problem significant to study? In terms of biometric systems, most of them have been monolithic in nature until now. But as distributed architectures become more pervasive, you'll have system use that can occur in different physical locations. An example is the ATM network. If you want to take, for example, PEFQ. PEFQ has ATMs all across campus. Now, for a user to be able to use the fingerprint sensor on a particular ATM, he or she should expect similar results when they use a fingerprint sensor on a different ATM. Well, this brings to light the issue of interoperability. What happens when you talk about a bank like Chase, which is across the nation? You cannot expect them to install the same fingerprint sensor across all the ATMs across the nation. So this problem will grow in significance as biometrics become more pervasive, especially within a distributed architecture realm. Just some definition of terms that I'll be using quite often throughout the presentation. The first is interoperable datasets, and these are defined by datasets that are created by collecting fingerprints on 2 different types of sensors. So when I talked about the processes with a biometric system, you can have enrollment or you can have recognition. So when the enrollment and recognition of the same individual happens on different fingerprint sensors, the resulting images basically comprise what is called an interoperable dataset. And a native dataset is one where the enrollment and the test images are collected from the very same sensor. And the false non-match rate, which was the primary metric that I used for measuring performance for my study, is defined as the proportion of genuine comparisons which are incorrectly rejected as imposter comparisons. So this is when a user cannot actually access the system as a genuine or the authorized individual. So the purpose of the study was to create a statistical analysis framework to examine the effect of these sensor-dependent distortions and variations on the false non-match rate of interoperable datasets. There are numerous metrics that can be used to measure performance of a biometric system. I chose to look at the false non-match rate, which is similar to a verification process. So you have another metric called the false match rate, which is the ability of the system to discern imposters from genuine people. And the second purpose was to analyze the impact of minutia count and image quality and skin characteristics on the performance of these interoperable data sets. Like I discussed at the beginning, image quality has an impact on performance. So these different fingerprints that are collected from different sensors might not be similar in image quality. So what kind of an effect does this have on the final performance of the data set? This is just the purpose of the study in a graphical format. There were fingerprints that were collected across 9 different sensors, and then the data sets were divided into enroll and test data sets. When the fingerprints were collected, the sensor characteristics were noted. Once a feature extraction happened, the fingerprint features were measured, and the final step was the matching operation. This is where the native dataset error rate and the interoperable dataset error rate were compared. And the idea was to look at sensor characteristics, fingerprint features, and the false non-match rate from a holistic perspective. So, like I mentioned before, there were 9 different fingerprint sensors that were used in this research, and all the fingerprint sensors provided images that were 500 dpi resolution. This was a decision that was made to create a baseline for all the fingerprint images. There were four sensors that were of optical touch type. There is only one commercially available thermal swipe sensor, so that was used for the study. There were 2 fingerprint sensors that were of the capacitive swipe type, and all laptops that come equipped with fingerprint sensors, the technology that they use are capacitive swipe. So and there were 2 other sensors that were of capacitive touch type. So the idea was to try and have sensors that would fall into the 3 different types of categories for the variations and distortions: the interaction type, the technology type, and the different designs. And the criteria for choosing these sensors was that they all had to be commercially available. One of the underlying themes of this study was to make the results pertinent to industry, and to basic science, so that they can actually devise systems that can be used better in the field. This is just a snapshot of all the different softwares that were used to collect the fingerprint images. Unfortunately, a single software could not be used to collect all the fingerprint images, so I had to use five different ones. And when I talked about fingerprint characteristics, I collected temperature, moisture content, oiliness, and elasticity of the finger skin before a user interacted with the fingerprint sensor. And these were the 2 devices that were used to collect those measurements. On the left, the device that you see collected the moisture, oiliness, and elasticity, and on the right you see a device that captured the temperature on the finger skin. Just a few of the important assumptions, limitations, and delimitations of the study. The assumptions were that all participants were treated as cooperative users, so they were not maliciously trying to provide fingerprint images of bad quality or trying to interact with the device in a wrong way intentionally. And the integrity of the commercially available products was considered to be consistent with their product specifications. So that was the baseline. The delimitations of the study was data collection was performed in a single visit. So there was no time gap between enrollment and verification attempts, and the environment conditions were controlled, since one of the scenarios that this study was trying to simulate is kind of an office environment where you as a user would get to interact with the device when you try and log onto your computer or log onto some kind of a network resource. And all users were allowed to do a practice session. And the idea behind the practice session was so that people who have not interacted with fingerprint devices before have an idea of how to interact with the device. And one of the limitations kind of goes off the very last point I talked about. that the experience of participants with fingerprint sensors was different. And as I mentioned earlier, interaction and habituation has an impact on how well do users, or not how well, but what kind of fingerprint images do users provide to the system. So this was an important limitation, and we tried to control this by allowing all users to have a practice session with it. So in terms of the variables that were collected for the study, collected the demographics of the participants, age, gender, and their ethnicity, and what would they say is a wear and tear on their finger. Their own subjective criteria was used. We collected the fingerprint images from the 9 different sensors and collected the finger skin characteristics like I mentioned earlier. Some of the important variables that were controlled during the data collection, we controlled the lighting level. Lighting has an effect on optical sensors because of the underlying technology. So we tried to simulate lighting that would happen in an office, a controlled environment. The temperature and the relative humidity also have an impact on the type of fingerprints that you provide to the system. So again, those were controlled in specifications with office environment conditions. And the sensor surface was cleaned before the start of each individual session. This was done to ensure that there was no residue or no remnants left behind from the previous subject, so that when an individual provided their fingerprint on the sensor, you would not get any kind of an underlying reflection effect from the previous interaction. I don't know how, okay, that came up better than I expected. So the data collection protocol, just to step you through it pretty quickly, the subjects were introduced to the study. Then we had to go through some ceremonial process of introducing to the study. We also have to comply with ethics, with the ethics board, because this is human data. So we had to get their consent. And once all the administrative work was done, the users got to interact with the device in a randomized order. So no two subjects interacted with the devices in the same order. This was done to actually control what is called the learning effect. And as users interact with the devices, if they interact with the devices in the same order, you'll see that they end up providing better images towards the end of the study. So this was done to control and minimize that effect. Then before they interacted with each sensor, their finger skin characteristics were measured. We also collected the force, how much force was applied on the fingerprint sensor when they interacted, and we collected 6 fingerprint images from a particular sensor. The first 3 images were separated into an enrollment dataset. The last 3 images were separated into what was called a test dataset, and then the user basically repeated that entire process until they were done with all the 9 sensors. So in the end, I collected data from 190 subjects. There were 9 sensors, and on each sensor they provided 6 images. So in total, we had 10,260 fingerprint images at the end of the study, and the entire data collection time period was about 3 months. 3 full months of data collection before we could actually go ahead and do the data analysis. This is just a photograph of the setup. Towards the left, you see all the 9 sensors that were used, and on the right, you see the fingerprint sensor that was placed on the force plate. And in the center of the force plate, you'll see a Velcro strip. This was done so that the user could place the fingerprint sensor on the force plate, so that, and when they interacted, it wouldn't move. So this was to fix the sensor to the force plate. Just a description of the participants. There were a total of 190, and the male and female breakdown wasn't equal, but 131 subjects were male, 59 were female. And since data collection happened here on Purdue campus, you can expect most of the participants to be under the age of 30 years, which which was what was noticed, and predominantly everyone was right-handed. Again, fingerprints from all the subjects were collected from their dominant hand only. So that was again done to control the difference in interaction between subjects if only their right hand or their left hand had been specified. So now going into the data analysis methodology, there were three main components. The first one was looking at the minutia count analysis. The second looked at the image quality analysis, and the third was the false non-match rate analysis. So for the minutia count analysis, we use a commercially available software, and the hypothesis that was tested was that minutia count for the data sets collected using these 9 sensors was statistically similar. That was a null hypothesis, and the alternate hypothesis was that the minutia count for the 9 different data sets was not similar. Here I have the minutia count tabulated. You can see dataset S1 had a minutia count, average minutia count of 72, and dataset S5 had the lowest minutia count, which was 29.16. So here itself, you can notice quite a range in the differences in minutia count for data sets that were collected from the very same individual, but the only difference was that they were collected on different sensors. A parametric F-test was performed to actually test the hypothesis, and with the results, we concluded that we rejected the null hypothesis, and we concluded that the minutia count for the data sets was actually different between these nine different data sets. So the parametric F-test told us that these 9 different data sets were not similar in its minutia count, but it did not really identify which pairs of data sets were actually not similar. So basically a full pairwise comparison was performed. And the way to interpret this table is if the value is less than 0.05, then that particular pair was not statistically similar in its minutia count. And if the value is greater than 0.05, then the pair being compared is actually statistically similar in its minutia count. So what you see here there were 3 pairs, S3 and S4, S2 and S7, and S6 and S9, that were actually statistically similar in its minutia count. And out of these, only S3 and S4 were of the same type. All the other pairs were actually collected from sensors that were of different technology types. So the next step performed was a very similar methodology, but here we looked at the image quality of the data sets, and the idea was to see if the mean image quality scores for these 9 different data sets, are they statistically similar or not. And again, looking at this table of the average image quality scores, you can see dataset S1 had the lowest image quality score, and dataset S5 actually had the highest image quality score. If you actually relate this back to the minutia count table, S1 actually had the highest minutia count, and S5 had the lowest minutia count. So there's obviously some kind of relation between minutia count and image quality going on. Again, with the parametric F-test that we did on the entire data set, we concluded that the image quality scores were in fact different between all the 9 data sets. So the next step was to actually drill down and see which pairs of these data sets were statistically similar and which ones were not similar. The way to interpret this table is exactly the same. The numbers that are greater than 0.05, those pairs were statistically similar, and all the numbers that were less than 0.05 were not statistically similar. So there were five pairs that came up to be statistically similar in their image quality scores, and the only common pair between minutia count and image quality that were statistically similar was S3 and S4, and you can see that S3 and S4 they were both of optical touch type as well. So once the minutia count and the image quality analysis was done, the final step was to actually see its impact on the performance of the system. What happened to the false non-match rate when you actually compared the native data sets to the interoperable data sets? And here you just see a schematic of the process that was performed to calculate the false non-match rate. To the left, you see the matching operations that occurred. To the right, the matrix that is shown on top, all the cells along the diagonal that are highlighted in blue indicate the native data sets, and all the cells that are off the diagonal basically indicate interoperable data sets. And using the match scores, the false non-match rates were calculated for these native and these interoperable data sets. Again, the idea behind this matrix was to be able to see all the results in a single tabulated format. I know there's quite a lot going on in this matrix, but I'll try and point out the interesting results from this. So along the diagonal, you see all the native data set error rates. This is where enrollment and test images were captured using the same fingerprint sensor. Now, for the combination of S5 and S9, that dark orange box that you see, what was noticed was the interoperable data set had a lower false non-match rate than the native data set itself, which was very interesting, because typically you would notice that the native data sets itself should have the lowest false non-match rate, but here the interoperable data set had a better false non-match rate. So that indicated that there was something interesting happening in there. And the cells that you see in blue, the vertical and the horizontal cells, a very high false non-match rate was observed for all the interoperable data sets that were formed with S8. But the native error rate actually seemed to be in line with some of the other native error rates that were observed. So this very clearly indicated that something was going on with the S8 dataset, which was not observed with the other datasets. So the previous matrix identified a way of looking at the false non-match rates, but just looking at the numerical value of the false non-match rates tells you which one is better and which one is worse. But in terms of statistical similarity, it does not tell you a whole lot. So in order to see which error rates were actually statistically similar, a test of homogeneity of proportions was performed. And if you're interested in reading more about it, it's called the Maresciulo procedure. You'll find plenty of documentation and literature on this particular methodology. So the idea was to see which pairs of data sets actually had statistically similar error rates. Again, the way to actually read this particular matrix is similar to the previous ones. If the values are less than 0.001, then the two pairs were, or that particular pair was not statistically similar. But if the value was greater than 0.05, then the pair was statistically similar in its error rates. So what was observed here was the data sets that were formed using S9 seemed to be statistically similar with all the other data sets. And we noticed that S8 was not statistically similar because they had error rates of 98 and 100%. So that was kind of a given, looking at this particular data set in this methodology. But you also notice that S2 and S1 had statistically similar error rates. Going back to the image quality and the minutia count analysis, this particular pair did not show a statistical similarity of minutia count or image quality. So again, there was something more going on than just the impact of minutia count and image quality on the final error rates. So in order to further drill down and see what else was going on with these data sets, a consistency of placement measure was created. And like I mentioned before, the interaction with the different sensors can lead to inconsistent placement. So we decided to look at the metric of consistency, which was if a core is detected in a pair of fingerprints, then that particular pair of fingerprints is said to be consistently placed. Now, what is a core? The core is defined as the point that is on the innermost ridge of the fingerprint, or the point on the fingerprint ridge with the maximum curvature. These are two commonly used definitions of the core. And why is this important? So towards the top left, you see the core was detected in both images, where the samples came from different sensors, and that was correctly verified. Towards the top right, you see the core was detected in only one image, and the samples came from different sensors, and it was incorrectly rejected because of inconsistent placement. And towards the bottom, you see that the core was detected in none of the images, but the samples came from the same sensor, and we saw that the pair was correctly verified. So there was some kind of a relation with the impact on, or the consistent placement on the error rates. So then we just created a scatter plot of the percentage of pairs of prints with cores detected versus the false non-match rate for the interoperable datasets, and we saw a trend where the higher the percentage of pairs of prints with the core detected, the lower was the false non-match rate. So there was a clear relation between consistency of placement and reduction of the false non-match rates. But there were two points that were outliers, and the data sets S6 and S1, and S1 and S6. So that those two were clear outliers to this phenomenon. So then we looked at the impact of image quality on interoperable false non-match rate, and the idea was to remove the lowest quality images from the interoperable datasets and see what kind of an impact it had on the false non-match rates. The idea was that if you remove poor quality fingerprints, then you should see an increase or an improvement in the performance. So let me just quickly skip through this. This was just the numerical analysis. The test of homogeneity of proportions was rerun on this new data, on these new false non-match rates for the data sets that had good quality fingerprints. And we did notice an improvement in the false non-match rates in absolute terms, but in relative terms for pairs of data sets, we did not really see an improvement in the false non-match rate. And what we were hoping to see was that data sets would be more statistically similar in their false non-match rates once we removed the poor quality images. But in fact, we noticed the opposite. There were more data sets that were not statistically similar in their false non-match rates when we removed the poor quality prints. And dataset S6 and S4 and S6 and S7 actually identify those. So once we looked at the image quality issues, the final step was we looked at the deformation model. This went back to looking at the S8 data set, which had a very high interoperable false non-match rate, but a very low native false non-match rate. So the image quality scores for dataset S8 and the minutia count analysis did not really show deviation from any of the other datasets. Consistency of placement also did not reveal any specific issues because S8 actually had really high consistency rate of placement with other interoperable datasets. So then the idea was to create a ridge spacing profile which measured the distance between successive ridge lines. So the process, just again a very general overview, was to skeletonize the fingerprint image, detect the position of the core, and traverse 100 pixels in the y direction and detect the change of color from white to black. So that is essentially detecting a ridge line. Use the IM profile procedure in MATLAB. It's an inbuilt procedure, and you see the output along the y-axis. On the left, you see a fingerprint image from the S8 dataset. On the right, you see a fingerprint image from the S3 dataset. And if you look at the graphs, the spikes indicate where ridge lines were observed in the fingerprint image. And you see that for the S8 image, the ridge lines were observed a lot closer compared to the S3 dataset. So then the S8 dataset was basically transformed so that its ridge spacing profile was more similar to the S3 dataset. And once that was performed, the new dataset was called S8 prime. The false non-match rate dropped dramatically from 100% for its original dataset to 6.43, as you can see in the table with the yellow boxes. So the S8 prime and S3 dataset actually showed quite a reduction. But the S8 prime dataset also showed a reduction in false non-match rates with the S4 and S9 dataset, which was pretty dramatic. And looking upon further analysis, we saw that there was a transitive property, there was transitive nature to this phenomenon. S3 and S4 and S3 and S9 had the lowest interoperable error rates. So when S8 prime was changed so that it would match well with S3, it also matched well with S4 and S9. So some of the conclusions that we had from the study, the minutia count similarity between data sets did not show a relation to a specific acquisition technology or an interaction type. But we did notice that similarity of image quality was more common among fingerprints collected from the optical touch sensors, and this might have to do with the fact that they were all touch type sensors. The similarity of minutia count and image quality did not really have an impact on similarity of false non-match rate, but it did have an impact in reducing the absolute false non-match rates for the interoperable datasets. And one of the datasets that actually stood out was the interoperable datasets of S9 had similar false non-match rates to the native datasets, but S9 did not really show similarity of image quality or minutia count. So that was one of the interesting conclusions. We also noticed that the interaction type and the false non-match rate were more positively related compared to the acquisition technology. This was when the data sets were actually regrouped just by the acquisition and the technology type. And consistent interaction had a positive impact on reducing the false non-match rate, which was, and that impact was also seen on interoperable data sets. We noticed that removing low-quality images did not really make false non-match rates more similar. So one of the avenues of further research is to look more deeply into what's going on, what types of variances are reduced when low-quality images are removed from the data sets. And consistency of ridge spacing seemed to be the most important factor. So that is one of the main future works that has come out of this is to develop a detailed ridge spacing profile, which can be used in a more sensor agnostic transformation process. Right now, a lot of distortion compensation models have been created, but they heavily rely on sensor characteristics. What kind of sensor was the particular image captured from? We are trying to create a sensor agnostic way of doing distortion compensation. And like I mentioned before, the performance metric used for this study was false non-match rates. Future work and work going on right now is looking at how does the false match rate, how is the false match rate impacted by these native and interoperable data sets. And we collected a lot of skin characteristics for this study, but we didn't really get a chance to analyze them in depth. So skin characteristics have an impact on image quality. So the idea is to look into how do you control the skin characteristics so that you provide better quality or more consistent quality images. That's the end of this presentation. Tried to give you a very brief overview of the work that was done. And if you have any questions, I think there's five more minutes left.
So maybe I have a question if nobody else. So, and what else can one do to improve interoperability of sensors? I mean, you mentioned one direction in your work, but are there others?
So, looking at this work, and not a whole lot of work has been done in this area. The consistency of placement seemed to be a very important factor in improving interoperable dataset rates. Also, usability issues. So that ties back with consistency of placement. But the rich spacing profile that we are looking at seems to have the most impact on improving interoperability.
But then how can one make sure that the placement is consistent? I mean, how can you do that?
And that is a very important question. Some of the work that's being done is how do you make the user design more intuitive so that when the user actually approaches the device, they know what to do, how to interact with the device, what kind of feedback is the system giving the user so that the user can change their placement if they need to. So until now, a lot of work has been done on improving the metrics side of the biometric system, and we are trying to bring the focus back onto the human, the bio side, so that there is interaction between humans and the systems. We need to look at both those components to actually improve performance of the overall system.
Okay, so
you said you weren't looking at algorithms, but what do you know about those? Would you say that there are probably 9 different algorithms and 9 different devices?
In terms of matching algorithms, yes, I would say that there are at least nine different matching algorithms, but they all the way they actually use the minutia points is what is different. The way they do the detection of the minutia points and the characteristics used to define the minutia points is a standardized format. But then internally, they all use these minutia points differently. Some use graphing algorithms, some use Euclidean distance algorithms. So how they use these minutia points is dependent on their application.
Do you know of anyone who's doing what you're doing, but studying the algorithms?
We have one of my other committee members, Dr. Hail Kim from Inha University in Korea. He has a couple of PhD students who are looking at distortion compensation using the algorithmic perspective so that interoperability can be improved from the system perspective.
Other questions? No. Okay, thank you.
Thank you.
Anyone else need to slide?